Okay, now let us do one problem on the concepts that what we have or learned so far. Okay. Now, the problem is given here in the slide. It reads like this: a peptide X of molecular weight 1320 1320 failed to react with Sanger's reagent. Okay. That is the number one observation. The second is the amino acid analysis. Now, what is meant by amino acid analysis? That means, if you have a protein or peptide, what are the amino acids that are present in that peptide? No sequence business, only the amino acids composition which is there in the protein, and then what is the number, what is their ratio. Okay. That means, you basically hydrolyze the entire protein and then try to see what is the concentration, whether there is lysine present or whether there is proline present, and what is their ratio, molar ratio. So, that is what is called amino acid analysis. Okay. So, amino acid analysis will give you the amino acids that are present, again just repetition of the same statement. So, amino acid analysis gave the following composition of the peptide. Phenylalanine, there is one, valine is, there are two molecules of valine, there is one molecule of proline, two molecules of lysine. So, I write it here. So, what is basically there is that you have, it says that X, first of all, it does not react with Sanger's reagent, that is number one. The second is that its molecular weight is 1320, that will be required, and then you have amino acid analysis, amino acid analysis. So, if you have amino acid analysis, then you see that there are there is one phenylalanine F. Now, we can write the one letter code, there is valine, there are two valines, there is one proline and there are two lysines. Okay. So, two lysines. Now, what are the other observations is that if you hydrolyze, go to the slide, if you hydrolyze this molecule X on treatment with trypsin. So, tryptic hydrolysis gives another peptide Y. So, that means, if X is hydrolyzed by trypsin, you get another peptide Y, and this Y, now you can do the partial sequencing. Partial sequencing means from n terminus you can determine one after another, and it says that if you do Edman on this, you get a sequence, and the sequence is like this, that first is phenylalanine, the second is valine, and the third is lysine. Sorry, I think this is lysine is actually K, that is the symbol for lysine. So, this is the first three amino acids in the peptide Y. The peptide Y is basically a derivative of peptide X by the action of trypsin. So, now assuming the average molecular weight of an amino acid, means if you take all the 20 amino acids and do an average, you will see that the number comes close to 110. This is the average molecular weight, 110. So, what is the structure of X? That is the problem. What is the structure of X? Now, how to solve this? First of all, let us find out how many amino acids it has. Now, the analysis that gave is basically that it has got two lysines, that means two amino acid here, then 3, then 5, then 6. 6 amino acids are present according to amino acid analysis. Remember, amino acid analysis will give the presence of the amino acids and their ratio. It is not absolute values, it is like empirical formula versus molecular formula. So, this has got these amino acids in these ratios 1:2:1:2. That does not mean that this is the absolute value which is present in X. Number of amino acids in X is given by 1320 is the molecular weight. So, you divide by 110 average molecular weight of amino acids, and that gives you a number of 12. That means, this is a dodecapeptide, that means 12 amino acids are present in X. Okay. 12 amino acids are present. Now, it does not react with Sanger's reagent. So, this X has to be a cyclic peptide, because there is no N terminus. If there is an N terminus, Sanger's reagent would have reacted. So, this is a cyclic peptide. The next point is, so we have now taken care of this point, we have now taken care of this point, we have also taken care of, we have not written any sequence here, but we have noted that this is just basically the ratio of amino acids. The absolute values actually of X will be 4 Ks, 2 Ps, 4 valines and 2 phenylalanines. That will make 12 amino acids. Okay. So, this will be the schematic structure of X. And now, when you treat with trypsin, so cyclic peptide will be cleaved. Obviously, X is what? X, this is the empirical formula, and the molecular formula becomes double of this. That means, this molecule, whatever sequence is there, that is going to duplicate like this, and then they are joined together and to give the X. So, when you treat with trypsin, so trypsin recognizes basic amino acids, and there is basic amino acid, that is lysine. Okay. That is lysine. Now, the question is, it is definitely cleaved somewhere, it is definitely cleaved, and it is cleaved because lysines will be, because it said, I say that this is because it is the doubling of the whole thing. So, there will be at least, there will be 2 cleavages in this whole circle, and if there is 2 cleavages in the whole circle, what you get? You get 2 pieces. If there are more number of cleavages, although there are 4 lysines in actually X, but you are, I am saying that there cannot be 4 cleavages, because 4 cleavages will, the problem will be the 4 cleavages cannot give the same, this same sequence, amino acid composition of Y. By the way, I think that line I also said that peptide Y has same amino acid composition like X, like X. So, okay. So, that means it has also got F and then 2 V, then proline and then 2 K. So, if that happens, same amino acid composition, so it must be then made up of 2 units of this, of same amino acid composition. So, it must be then, it must have been cleaved like this to give 2 pieces which have got same amino acid composition. That means, they look the same. Okay. They have the same amino acid analytic composition, as well as now the question is whether they have same sequence or not. Okay. But it is only one product. Why? You are not getting 2 products. So, that means, they have the same amino acid same amino acid analysis results, as well as they have same sequence. Otherwise, you would have got 2 products here by adding trypsin, but that you are not getting. Okay. So, that is the once you have sorted out that, now let us start drawing the structure of Y, because Y you have got a partial sequence, that F is there, then valine, then lysine, up to that point is there. Now, the next is what are left now? You have already taken care of F, you have already taken care of one valine, and you have already taken care of a lysine. Now, what is remaining is the one valine, proline and another lysine. Okay. Now, if you, that means, you have what is left here is a proline, a valine and a lysine. Okay. Now, I have now different options here. You can write many different, that A V K you have to, that is fixed, because that is the partial sequence, and then if it is followed by say a valine and then a proline, then a lysine, if that may be the case, there are a lot of permutation combination now with PBK, but if somebody is very intelligent, he can immediately say that there must be a proline, because there are 2 lysines here in Y, there are 2 lysines in Y. So, the 2 lysines are expected to be cleaved by trypsin, but that is not happening, because Y is Y is only this piece. This is Y, another piece of Y, but both are same. Okay. So, if the Y is cleaved again by the lysine, there are two lysines present in Y, remember, but you are getting only one cleavage on two sides. So, if that be the case, then there must be a proline which is after the lysine, because only if that happens, then you have got only another lysine is kept which can induce the cleavage only once. Okay. See, the other way, if you want from the very beginning ab initio, then there is a lot of wastage of time, because you can start writing many sequences, that A, B, K, suppose after this I put V, K, P. So, this is Y, that is one possibility. Now, whether this will be correct or not, that is a question. In this case, what will happen, that there will be a cleavage here, because this is the lysine, however, there will not be any cleavage at this position. Okay. Then you can have another sequence F, B, K, then K, V, P, all these things are there, but I will as I said, you can continue on this, but then it will take a very time consuming route, but apply your brain that the F, V and K that was there, and then you try to put a proline to stop the breakage within Y, to stop the breakage within Y, that is very important. If you do not put proline here and if you put valine here, that means there should have been any cleavage here at that point, but trypsin is not doing that. Trypsin is giving the entire the 6 containing amino acids. Okay. So, that is the tricks here, and if you do that, so that is the proline. Now, you are left with only 2 amino acids, one is valine, another is a lysine. Now, you have two possibilities, valine, lysine, that is one possibility. The other possibility is F, B, K, P and then K and then V. Remember, this is your N terminus and this is your C terminus. Now, what we have to do to dimerize it, that it will be just the opposite way you write, that this will be K, this will be V, that will be P, that will be K, that will be V, that will be F, and then this will be CO and that will be your NH. Okay. So, this is one possible structure. The other possible structure is coming from this dimerization or cyclic structure of this. So, you write the opposite one, that might be better, might be easier to understand. First write from the opposite side V, K, P and then K, V, F. Okay. And then this is your NH, this is your CO, and on this side this is your CO and that is your NH. So, this runs from, this is the N, could have been N terminus. Now, there is no terminus in that sense, because it is a cyclic one. So, it is going like this. We started with F, thinking that the NH2 on this side and the carboxy on the other side. So, either this is X or either this is X. Now, which one is correct? So, now you see trypsin, if you give trypsin, so where are the cleavages? This is a lysine. Remember, trypsin recognizes basic amino acids and it cleaves on the carboxy end of the basic amino acid. This is the two important points. There is a basic amino acid, but after this there is a proline. I told you, if there is a proline, hydrolysis will not take place. Then there is a valine and then followed by a lysine. Now, this is the one. After this there is a phenylalanine. So, this there is no problem. There is no proline after this lysine. So, there will be a cleavage at this point, the carboxy end of the lysine. And again you come back here, NH, this is in the opposite direction, and when you come to this part, this lysine, that cannot be cleaved because there is a proline here, but this lysine and it is connected to phenylalanine. So, now there will be a cleavage here. Now, you see that this actually matches. The sequence here is F, B, K, P, V, K, and the sequence here is the same, F, B, K, P, V, K. Remember, you have to read from this side, because this is the N terminus end of the lower chain. On the other hand, if this is correct, suppose, then what will happen, this will again will not be hydrolyzed because there is a proline, but this will be hydrolyzed. Okay. And where is the other hydrolysis point? The other hydrolysis point is this. Again you get this the same two parts. Here you get B, F, B, K, P, K, and on this side you get again B, F, B, K, P, K. Same. But where is the difference? Because our results say that the first three amino acids are F, B, K, but in this case the amino acids that will come out will be this B, then F, then V, then K, then P, then K. I hope you are understanding this. This is NH2 and this is CO2H, because now the breakage has taken place here. So, this is the first amino acid from this side and that goes up to this side, and this is the other way B, F, P, K. Yeah. So, only difference is that in this case the partial sequence will be this B, F, B, but in this case the partial sequence will be F, V, K, P, V, K. So, the partial sequence matches. So, this is the correct answer. Okay. So, that is, so this is a very tricky problem, a cyclic one which is divided into equal parts with equal parts having the same amino acid composition, and then with trypsin. Remember, trypsin does not discriminate between cyclic or acyclic, that also we have learned from here, but Sanger's or the carboxypeptidase, that will distinguish between the C terminus, whether there is a free C terminus or whether there is any free N terminus. Okay. Okay, so far so good. So, we just learned how to know the primary structure, and we have also sorted out one problem, and that is a more difficult problem. There are even simpler problems like the other ones, and in the weekly assignments we will give different types of problems based on the primary structure of proteins for the first week. Okay. Now, the next thing is, next question is, okay, it's well and good that if you have a protein, the first thing that you want to know is to know the amino acid sequence. Now, you just reverse the problem, that I want a protein or I want a peptide which has a particular sequence. Suppose I want to make a peptide which has got V and then A and then G. This is a tripeptide, valine, alanine, glycine. Okay. So, it is now the reverse problem. Earlier I had a peptide, I want to know what are the amino acids sequences. It is now the reverse problem, that I want to make a peptide with a defined sequence. I take a very simple tripeptide, I do not want to make it really big, very small tripeptide, because the historical way how peptide synthesis took place, it is only first they made the dipeptide, they are able to make the peptide bond. Now, I will first highlight what are the problems associated with this. We know that valine, what is valine? Valine is having a side chain which is isopropyl. This is valine. And what is alanine? Alanine is only a methyl as a side chain. And what is glycine? Glycine does not have any side chain. So, when I have written this VAG, that means NH2 of this is free and the CO2H of G is free. Okay. So, basically we have to combine these three. Now, you cannot combine all three in one go, that is not possible. So, you have to go step by step. First, let us there are two possibilities now. What I can do, I can combine V and A, so that I make a dipeptide VA, and then I add the G and to make the complete the synthesis as BAG. So, this is that should be my strategy, or the strategy could be that somebody might say that okay, I will first combine A and G. So, I will make AG and then I will add the V and to make VAG, that is also possible. From both directions you can synthesize the molecule. Now, the question is, in order to do this, the joining of say V, suppose we decided that first we will make Va. So, we have to join V and A, valine and alanine, and this joining is nothing but expulsion of a water molecule, and that should give a peptide bond CO NH and then the alanine, okay, COOH. I told you that the peptide bond formation is thermodynamically very favorable. It is the delta G is highly negative. However, there is a kinetic barrier, enormous kinetic barrier to do this reaction. That is one problem. You cannot just mix these two and you cannot just remove water from this. That is number one the problem. The second problem is, what is the guarantee that this NH2 will react with this carboxy, because this NH2 can react with another molecule of alanine. So, that alanine and alanine can combine and form a peptide alanine, alanyl alanine. So, also valine can do that. So, there are these self coupling that can take place. So, that is the second problem, and that is the third problem. The third problem is that these molecules are chiral. When you make a peptide, we are talking about making, generally we are making L from L amino acids. If you require D amino acid for some purpose, you can also start with D. But the question is whether you are integrating, when you are joining these two, whether your chiral integrity is retained or not. That means whether there is any percentage of racemization or not, because if there is any racemization, then your number of peptides will increase. L configuration of V plus L configuration L of alanine, okay. And if these two are joined, if there is any racemization L going to D, then you have a new peptide L configured V with a deconfigured A, or the vice versa, deconfigured V, the L configured A, or deconfigured V and deconfigured A. So, racemization is, so there are basically three problems. One is self coupling, how to avoid that. Number two is how to drive the coupling reaction, because it is, although thermodynamically favorable, it is kinetically unfavorable. Drive the coupling process. By coupling process, we are meaning the formation of the peptide bond. And the third is how to maintain the integrity, stereochemical integrity. Okay. So, these are the three challenges. Integrity. Okay. Now, to avoid self coupling, what you have to do? See, you want only the reaction to happen between this carboxy and this NH2, and you do not want any reaction between this carboxy with this NH2 or this carboxy with this NH2, because that will give AV, not VA. So, if that be the case, then what happens? So, what you have to do now? What is called the protection chemistry. See, you have to protect this amine so that it cannot participate when you are coupling this with this amine. So, this amine needs to be protected, okay. And at the same time this carboxy needs to be protected. Then once you have these protected things, protected the N protected valine and the C protected alanine, then your, if you do the reaction at the appropriate condition, then only you can have the combination of or the desired peptide bond. So, that is, so to avoid this self coupling, you have to protect these amino acids. Okay. Another good part of protection is that these amino acids are actually water soluble, they are not soluble in organic solvents. Okay. When you do synthesis, it is very difficult to do synthesis in water. Today everybody is searching of methods which can be done in water, that is what is called green chemistry. that is in the domain of green chemistry. Remember, enzymes work in water. Okay. That is why people are trying to mimic enzymes or use enzymes to do synthetic chemistry. But when you do peptide chemistry, this coupling, which is removal of water, you cannot do the reaction in water. If something is removed which is already present, you know by simple Larsa-Taylor principle that will not work. Okay. So, you cannot do it in water. By protection, what happens? These becomes soluble in organic solvents. So, your chemistry can be done in organic solvents. So, that is another advantage. The second one, how to drive the coupling process. So, when you want to couple NH2 and CO2H, now in the laboratory, what we do in especially the organic chemistry laboratory, if you are asked to determine or make an amide bond from a carboxylic acid, you know the way to do it is that make the carboxylic acid into an acid chloride by adding PCl5 or thionyl chloride or oxalyl chloride. So, that will become COCl. That means, you activate the carboxylic acid, and then if it is activated, the Cl is a very good leaving group. So, now the NH2 can attack the CO and the carbon of the COCl and the chloride will leave. So, basically what you need to drive this coupling process is activation of CO2H group. However, in amino acid chemistry you cannot use PCl5 or SOCl2. I will tell you why. Third problem is how to maintain the stereochemical integrity. You know the stereochemistry comes from this hydrogen. Epimerization of this hydrogen or a racemization of this hydrogen involves removal of the hydrogen, because this is quite acidic, and then again putting back into the same carbon, and while putting back you actually invert the configuration. So, one should not use highly basic, one should not use basic or acidic conditions. Mild acid or base may be okay, but one should not, one should avoid the aqueous like sodium hydroxide or potassium hydroxide or HCl. One should not, one should avoid those type of reagents in the entire process. Okay. That means, one should avoid harsh, I can write also this, harsh conditions, because racemization also can take place even if there is a very tiny amount of pH is almost neutral, but if you heat it strongly during the coupling process or any of these chemistry that we are going to describe, then also there could be racemization. So, that is why these are the three things. So, first what it says that I told you that our first business is that if I want to make the dipeptide between valine and alanine, what I want to do? I need to protect the amine of valine, okay, keeping the carboxy free. This is valine, and I want to protect the alanine carboxylic acid and keep the amine free. So, these are the things. So, that should be COO some protection group here, and that should be NH some protection group. These are different. So, it's P1 and that is P2. Now, what are these protecting groups? Again, as I said, harsh conditions have to be avoided in order to minimize or completely remove the racemization. So, you have to use very mild processes. The protecting groups of amines are, there are many protecting groups, but I will just show you the very common ones. NH2 protection is done by one is called, these are usually converted into what are called carbamates. What are carbamate? Carbamates are NH, then CO, then O and then R. This comes from carbamic acid. You know what is carbamic acid? That is NH2CO2H, which is very unstable, which loses immediately ammonia and carbon dioxide, but carbamates are stable. Now, so this amine has to be converted into a carbamate, and this R should be such that this can be taken off very easily. So, based on this, you have R is equal to T-butyl, tertiary butyl. That is one, and the other one is CH2PH. That means the amine basically is converted into NH, suppose it is CO, then O, then T-butyl is written like this, and this is your valine. So, the carboxylic acid remains there. So, this is protected as, this is called the T-butyloxycarbonyl. So, the amine has been protected as T-butyloxycarbonyl. So, this is commonly known as T-BOC group, tertiary butyloxycarbonyl. So, NH, because all the time you cannot write this structure, you can just write that my valine is protected as T-BOC. You just write like this. Sometimes T is in the subscript, sometimes it can be also taken here, but usually it is in the superscript, sorry. So, NH. Now, so this protection is done, or you can also make the benzyl. Instead of the tertiary butyl, you can also have benzyl, and then that will be called NHCO, O, and then CH2PH. This is valine. Okay. So, this will be called benzyl oxycarbonyl. Benzyl oxycarbonyl, unfortunately, this was earlier when it was discovered that this is a good protecting group for amine functionality. This was called carbobenzoxy. That is why this is called CBZ. Okay. You could have called it benzyl oxycarbonyl, but they do not call it benzyl oxycarbonyl because that will match with butyl oxycarbonyl. So, very difficult to differentiate between these two. So, that is why this is called carbobenzoxy, CBZ, and this is called T-BOC. Now, the one thing one must remember that in peptide synthesis, that the first step is protection of amine of one amino acid, carboxy of the other amino acid. Then you couple the two. But what is the third step? The third step is finally you have to take these protecting groups off, because you do not want protected peptides. You have to deep protect this. Okay. So, this is protection. Now, deep protection is this deep protects into the free amine again by organic acid like TFA. TFA is an organic acid. I said that that acid base should be avoided, but that acid base is usually I am talking about strong bases like NaOH or HCl. Those type of things are avoided. Organic acids are no problem, and also anhydrous HF. You know, HF is actually a very weak acid in the pure form. HF is a weak acid. You can use also HF. That is allowed, so long as water is not there. Okay. So, these are the T-butyl group comes off by treating with TFA. Usually TFA is easier because HF, you know, you need special apparatus. HF is the glass. So, you cannot do HF reaction in glass vessels. You have to do it in Teflon coated glass vessels. So, that is costly. So, usually in the laboratory normally we use TFA, very easy. TFA is much easy to use, and in the, so this T-butyl comes off with TFA, and the CBZ comes off. CBZ, that means this whole group comes off if you treat that with hydrogen using palladium charcoal, then this CBZ group comes off. That means one comes off under very neutral condition, another comes off with TFA. So, in a peptide, if you have both these groups present, say a tripeptide, where this is also present, this T-butyl, and this is also present, then you can selectively deep protect one over the other. If you use hydrogen, this will be deep protected. So, it will form the free amine, and if you add TFA, then this will form free amine. These are very important. That means, these two processes are orthogonal to each other. So, you can selectively deep protect one, keeping the other intact. Okay. So, these are the two protecting groups for the for the amine. So, next, what are the protecting groups for the carboxy? The protecting groups for the carboxy, remember in our case I have to protect the carboxylic group of the alanine. I have to use the alanine where the carboxy is protected. So, what are the protecting groups that are used for carboxy? The protecting groups are again under very similar way, that you have COO, it is converted into an ester, but not any ester, like R cannot be methyl or ethyl or those things, because you know methyl or ethyl esters have to be hydrolyzed to get the free acid. It has to be hydrolyzed using alkali or concentrated acid. So, this R cannot be methyl or ethyl. What is R? R is again either T-butyl CCH3 thrice, or it could be again benzyl CH2PH. That means the carboxy is protected either as T-butyl or as the benzyl ester. Remember, there are now lot of other protecting groups that are used, but I am saying you the most commonly used protecting groups. So, either T-butyl, that is one, or it could be benzyl COO CH2PH. Now, again their deep protection, this is the protected form. If you want to deep protect at the end of the day, so what are again the reagents are same. TFA will take care of this T-butyl ester, and hydrogen will take care of the benzyl ester. Okay. You will see the utility of this orthogonality of protecting groups when you have peptides of higher chain length, that means higher number of amino acids. Then you have to constantly switch back and forth of different protecting groups. Okay. So, I am not saying how these protecting groups are incorporated, that is possibly the next lecture I will quickly go at that time, that how the protecting groups are incorporated, because that is the first step, and the last step after all the coupling is done, then you have to deep protect. Okay. So, those mechanisms we can discuss in the next class, but right now we have a protecting group. Suppose we have put a protecting group here NH T-Boc. Okay. So, our valine is protected as a T-Boc, and the alanine should be protected, the carboxy should be protected. The question is which protecting group I should use. Now, this protection, I see the valine has been protected as T-Boc, which comes off with TFA. Now, if I protect the alanine with benzyl, I can do that. I can do and protect with benzyl and then do this coupling reaction. But then I will get a protected peptide, where to take the T-butyl off I have to use TFA, and to make the benzyl off I have to use hydrogen. So, that means I am adding more number of steps into my synthesis, which is not desirable. So, what we should do then? We should not use CH2PH here. It will be better that if we use T-butyl here, then what will happen, that after the coupling reaction here I can take both the protecting groups off at the last step. So, with a single step I can deep protect the molecule. So, all peptide synthesis, the protecting groups are selected in such a way that last step becomes a single step deep protection of all the protecting groups. So, at that time you should have protecting groups which are not orthogonal, which are similar type, which comes up under the same condition. Okay. So, the next part is the elimination of water, formation of the peptide bond. So, what to do? I said that what you need is basically to activate this carboxy. So, this carboxy must be converted into something which will be called a COL. L is a leaving group, and this NH2 remains as NH2, that is the nucleophile. And now this should be the reaction, the leaving group leaves. So, you get CONH bond. That is, in the laboratory, as I said, organic chemists make amides by making RCOCl and RNH2, and that will react. That reaction is very spontaneous, very vigorous. Those who have done this amide preparation, they know that immediately it forms the amide bond. Okay. So, initially what was tried to couple these amino acids is that convert this carboxylic acid into your RCOCl, okay, NH, TBOC, and then you have the valine here, and suppose I have converted it into RCOCl, plus you have this amine, NH2, alanine, and this is protected as T-butyl. And I told you why the two. You could have the other possibilities that you could have a CBZ group here, and then you should use a benzyl here. So, that last step is hydrogenolysis. Now, this, if you want to couple this will couple definitely, that is going to attack here and that is going to come out. Okay. Initially the negative charge goes on the oxygen, then it comes back and the chloride is kicked out. Okay. So, you get the peptide, but the problem is here lot of racemization happens. Lot of racemization happens because of side reactions. What are the side? What is the side reaction? That when you have this valine NH, just draw the structure of the T-butyl O. This is your T-butyl, and you have COCl. Okay. And what you want is an external nucleophile, that is the second amino acid going to attack here, that what you want, and you are expecting that. That will happen, no doubt, but alongside something else will happen, and that is before the external nucleophile attacks, just like your methionine cyanogen bromide reaction, this now comes to this bond, the oxygen is activated and that is going to attack the carbonyl and the chloride leaves. So, what is formed is N double bond this O, and then it is a lactone, and this is your valine, and this is the product OT-butyl. Now, this is called, this is a lactone, but this is called as a lactone, as lactone. This is called an azolactone. Okay. This azolactone, the amine again can come back. Means you can have reaction on the azolactone, that is also not very stable. So, that will come here and it will again go back to the T-butyl, that is possible. But this coupling reaction, that means it has got two mechanisms. One is it can directly attack the acid chloride and form the amide bond. If that happens, no problem, no racemization. But if it, in the meantime, if it goes to the azolactone and then the amine comes, the amine from the other amino acid comes and attacks the azolactone and then forms the amide bond, then there is a problem. The problem is in the azolactone, this hydrogen which was there earlier in valine, that is the where the stereochemistry comes. Na? This hydrogen becomes very susceptible as soon as it forms the azolactone. It is much more acidic than this hydrogen when it is in the acyclic form. And why is that? Because if you remove this hydrogen, acidity means if you remove this hydrogen, so you make a negative charge, and now you see this negative charge will conjugate with the carbonyl. So, you have a double bond here, that will be O minus, and what is the situation then? Then the whole thing becomes N double bond O and then O minus, and then there is a double bond. So, this, and then you have the valine. Now, this is what? This is an aromatic system, right? Oxygen lone pair and these be double bonds, two double bonds, that makes it aromatic. Okay. So, that means this hydrogen becomes extremely acidic, and by the time this RNH2 attacks this carbonyl, it has already, there will be some racemization that will take place before the attack of the external nucleophile. So, azolactone formation is a serious drawback of activating the acid group as the chloride. So, we should find a very milder version of coupling reaction, and that we will talk in our next lecture. Okay. So, what we have learned is basically that when you want to make a peptide of desired amino acids, then the first step is protection, the second step is coupling, and the third step is deep protection, and then you get the peptide, desired peptide. So, I just wanted to, I just highlighted some of these protecting groups, some coupling reagent, what was initially tried. I told you about this azolactone formation. I have told you how to deep protect also some of these protecting groups. Okay. Thank you. So, we will talk about other, we will go into deeper in the next lecture about all this coupling reagent, the coupling issues. Okay. Thank you.